Good afternoon, everyone. Thank you for being here. And it's a pleasure for me to introduce Mike McDonald, the speaker of this afternoon colloquium. Mike is now coming from super far away, as he's assistant professor at MIT. And he has been there for the last couple of years as a assistant professor, but he was there before as a fellow. He was a Hubble postdoctoral fellow there before. And I think he has been, it's not coming from far away, as he's just down the road, but Mike is originally from Canada, and he moved in the US 10 years ago to do his PhD at University of Maryland, and then it just went directly to MIT, and he's been there since then. And we have a lot in common, and we never met, but we discovered to be on many X-ray projects together, and he has a great experience is like in working group for the LINX mission, for the StarX proposal, and Athena, and also StrobeX. Mm-hmm. And today he's going to tell us about his work on galaxy cluster evolution over the past 10 billion years. Thank you.
Thank you. Can you hear me okay? Yeah, good. All right. Okay, yeah, so I'm going to tell you about some work we've been doing just down the road, but also a lot of this happened here as well, and wouldn't be possible without some great work and contributions from people here at CFA and all over the world. So thanks to everyone involved. So that 10 billion years should have maybe a little twiddle in front of it. I'll try to get out to roughly redshift 2, give or take. But the point is that we're pushing much further in redshift than we have in the past, and we're able to say a lot more about how galaxy clusters evolved over this time frame. So let me just start at redshift 0 with the basics. So what is a galaxy cluster? It's a cluster of galaxies. It's a group or an assembly of hundreds to thousands of galaxies, all mutually bound by gravity. As I said at the ITC talk this morning, galaxies and clusters are typically red and dead. There's processes in the cluster environment that drive galaxies from the blue cloud to the red sequence, such as gas stripping as galaxies fall into the cluster environment. So there's this trend as you increase the environmental density to go from blue to red. That's mostly unimportant for today. What is important is that at the center of the cluster, there's this one very important galaxy, which we traditionally call the brightest cluster galaxy, or the BCG, which is not a great name. I prefer to call it the central cluster galaxy, because that's what's important about this galaxy, is that it sits at the bottom of the gravitational potential, and as a result, it experiences a different life cycle than a galaxy that does not sit at the at the bottom of a giant gravitational funnel, right? So it has a preferred position in the universe, and as a result, it has a different evolutionary path than most galaxies do. So I'm going to come back later to brightest cluster galaxies. So just a warning. The bulk of the baryons in the cluster environment are in the intracluster medium. There's a lot of people here who work on studying the intracluster medium, so these might be familiar images to many of you. The hot plasma, the ICM, fills a megaparsec volume. It's roughly 10 to the 13, 10 to the 14 solar masses, and it's heated to about 10 billion degrees just by the very, very deep gravitational potential. The really neat thing about the intracluster medium, and which you can observe in the X-ray, is that it sort of retains an imprint of major energetic events in the lifetime of the cluster. And so long after signatures of, for example, merging disappear in terms of the galaxy population, you can see those signatures in the X-ray. So here's an ongoing merger. This is the bullet cluster. You see this shock front here. And you see that there's clearly two peaks to the X-ray emission. So this is two clusters that have smashed together. This is sort of like if you shot a bullet through a watermelon kind of thing, right? It's it's coming at the other side and it's kind of blowing up the whole thing. And so this is very clearly in the X-ray an ongoing merger. In the optical, it's not as obvious. Long after these galaxies settle down into more of a spherically symmetric distribution, you see those signatures in the X-ray. So this is a past merger, Bell 2052, and this is a sloshing arm. And so the gas, long after the merger is still sort of wobbling around in the same way that, if I had a wine glass here and I slid it across the table, the wine glass would come to rest, but the wine would continue to slosh around in that glass for quite a while. And in the same way, the gas sloshes around in the cluster, and so you can tell the history of the cluster for longer looking in the X-ray than in the optical. AGN, central supermassive black holes can blow bubbles in the hot gas in the same way that an aerator in a fish tank blows bubbles, right? And these bubbles will rise to large radius in the cluster, and we can see those bubbles, and we can actually answer the question, how much energy was needed, how much PDV work was required to inflate that bubble, right? And we can actually measure the power from the black hole without looking in the X-ray at all, or in the radio at all, sorry. And these bubbles are coincident with radio jets, and so we think they're being inflated by these jets. These are all interesting signatures, but if you see no morphological signatures, if you just see a smooth ball of X-ray gas, that is also interesting. Some of us get, very interested in these smooth balls of gas, right? Because these are systems that are probably in hydrostatic equilibrium, that are probably cooling very rapidly, probably aren't experiencing any, major disruptions, which allow them to sort of be themselves in a way. And so that's, on its own, just an interesting sort of morphological feature that tells you a very long story. Over, roughly a few billion years, no one has interacted with this cluster in a significant way. The intracluster medium, if you look a little bit deeper, is extremely uniform, almost to a boring extent. And so, almost any property you look at, cluster to cluster, you see the same thing, right? So if you look at the gas fraction as a function of radius, ignore the core, once you get out to about half of the virial radius, they all have the same gas fraction, and that's roughly the gas fraction of the universe. So clusters are actually, mini universes in a sense, and you can get a pretty good handle on the baryon content of the universe by just measuring the baryon content of a single cluster, which is kind of neat. If you look at the metallicity of this gas, again, you get outside the core, these all lie on a single value of a roughly 0.3 solar metallicity. The scatter here is purely statistical. There's no evidence for intrinsic cluster-to-cluster scatter in the metallicity of the gas. So every cluster you look at has a third solar metallicity, which is a little bit mysterious as well. If you look at the entropy of the gas, sort of the how kind of primed for cooling is this gas as a function of radius, again you get outside the core and they all collapse onto a single profile. So this is like 300 clusters that occupy almost no width here. This is just almost all statistical scatter. Right, so this is very, very uniform properties in three very different things: gas content, gas metallicity, gas entropy. Yet they all look the same, cluster to cluster. And so one of the big questions that we're going to try to answer today, and throughout my lifetime, is when was this uniformity established? Right, this is one of the big questions. Clusters at redshift 0, if you've seen one, you've seen them all in a sense. And maybe that wasn't always the case. And so we want to try to get at when were each of these little bits of uniformity established. In the centers of clusters, things are a bit more interesting, which is why that's where I usually work. So you see all of these things, the spread blows up in the center, right? And so part of the reason for all this uniformity is that gravity is the dominant process in the cluster environment. That's why clusters are self-similar, because gravity does basically all the work. But that's not true in the center. In the center, there's other important physics, right? There's baryonic physics processes, or there's cooling and heating and other things happening in the center, and that's driving the scatter, and that's making individuals unique essentially. And so this is why you get different systems that look vastly different in their cores, but can look very similar in their outskirts, is because the physics is a little more exciting in the centers. In the centers of clusters, we typically divide up these systems into two types to kind of reduce some of that scatter. So the two types are what we call cool cores and non-cool cores. They're not very creative titles. The cool cores have cool cores, and the non-cool cores are not that. It's very simple. So these are X-ray images of 3 cool cores. You see they're all circular, so they're relaxed clusters that haven't experienced a recent major merger, and they're all very centrally concentrated. The color scheme is such that white is high surface brightness. These are non-cool cores. They do not have the white center, and maybe by coincidence, they're all also not circular, right? So maybe it's that merging can destroy a cool core cluster. The jury's kind of out on that. But none of these systems have this sharp peak in the center. That's the important bit. If you turn this into a 3-dimensional image, just for fun, where X and Y are on the plane of the sky, the cool core has this very sharp density spike in the center that the non-cool core doesn't. And I haven't plotted, a cluster versus a group to make this dramatic. This is the coma cluster. This is a very, very massive X-ray bright cluster. It just doesn't have this delta function in the center. So the size of this is about 100 kiloparsec, but inside of 100 kiloparsec in coma, it's basically just flat X-ray. There's no cusp like this. And so what does this cusp actually mean? Well, because the X-ray surface brightness is high, and this is radiation, this is energy being lost by the plasma, that means the cooling is high, right? If you throw away more photons, then you're cooling faster than your neighbor, right? And so this spike in surface brightness, or the spike in density, is really a spike in cooling rate, because the cooling goes like density squared. And so if you see a spike in density, you're seeing a spike squared in cooling. And so this central sort of icicle-like thing, that should all cool in roughly 1 billion years. And there's a lot of mass in that icicle. So this is what we call the cool core, and the cooling time, inside that 100 kiloparsecs is roughly 1 billion years. And so this led very quickly to a thing that we call the cooling flow problem, or the overcooling problem. So if you imagine a big ball of gas, megaparsec ball of plasma, and you just leave it alone, the fact that we see these systems in the X-ray means they're losing energy, they're radiating away energy to us, and so that means they're cooling. The cool gas will sink towards the center where the density is higher, but cooling goes like density squared, so that's a runaway process, right? And so this gas very quickly funnels in towards the center, reaches very high density, and then cools out to the molecular phase and ignites a massive starburst. And so let's all go out and look for starbursts in the centers of clusters, because that's what should happen. So this was, these cooling flows were sort of postulated around the early 90s, and people went out and they didn't see these massive starbursts in the centers of clusters. And so that became known as the cooling flow problem. And so you can get at that problem a different way. If you just go out and count up the number of galaxies of a given luminosity, I love this plot because it's a hand-drawn plot that was actually in a paper. And I'd love to try to hand draw a plot and get it past a referee at some point. So this is the number of galaxies above a given luminosity as a function of luminosity. The blue curve is observations, hand-drawn, but roughly observations. The red curve is theory. So if you just go out and count the number of halos above a given mass, that's this red curve. And so we have too few low luminosity galaxies and too few high luminosity galaxies. And so that means that star formation is inefficient in low mass galaxies and high mass galaxies. In low mass galaxies, the reason for this is because the potentials are very shallow. So you make some stars, those stars go supernova, those supernova blow out the gas never comes back, that doesn't turn into stars, and so your luminosity is low. And so I apologize if anyone works on dwarf galaxies, and I probably really oversimplified that. But the point is, this is probably just shallow potentials. It's easy to get rid of the fuel for star formation, and so you'll have less stars. In these cluster galaxies, so these high mass galaxies live in the centers of clusters. These are the brightest cluster galaxies I talked about on slide 1. These most massive galaxies, the potentials are too deep for supernova to blow the gas away. And so removing the fuel for star formation is not an option. And so the only way to prevent that gas from turning into stars is to just keep it hot forever, right? So if you can't get rid of it, just hold it back basically as long as you can. And so the idea here is the AGN feedback keeps this volume of gas hot, and so the gas just never quite cools. Which might seem a little bit shaky, but if you actually go out and do the measurement, right, and you say how much energy is being radiated away in the X-ray by these cool cores, so how quickly is the gas cooling, versus how much energy is being put back into the system mechanically by these pistons, these radio jets, right? They're dumping energy into the cluster, and there's this nice correlation. I should really update this plot. This is 11 years ago now. There's a lot more data points to put on this, and the point is that the more cooling that should happen, the more feedback we observe. And so there's this very nice tight correlation between energy lost by cooling and energy put back in by the AGN. And so this cooling gas is kept at bay for a very long period of time. And I'll play spoiler here. It turns out for about 10 billion years, it looks like. But we'll get back to that. So this makes it seem like everything is just perfect and all the cooling is kept at bay. But if that was the case, I wouldn't have a PhD, because my PhD was answering the question, how much cooling actually happens? And so it turns out a very, very small amount. I'd probably still get a PhD, I think. Non-detections are important. If you go out and count up how much stars are being formed in the centers of clusters, you're not seeing these huge cooling flow fueled starbursts, but you are seeing some star formation. So these are H-alpha images of the center of a few clusters. You might recognize some if you're in the field. And so there's a lot of clumpy filamentary star formation happening in the centers of these clusters, but it's 1% of the prediction. So we see all this cooling happening in the X-ray, and then we go and look for it in the cool phase. So at 10 million degrees, it's cooling, and then we close our eyes for a while and we look at like 10 degrees, and 1% of it is there, right? So 1% of that 10 million degree gas actually makes it down into stars, and 99% doesn't. And so this is, the crux of the cooling flow problem. But the point is, this 1% is not zero. We do see a trickle of cool material that lands on the BCG and forms stars, which will be important a little bit later in the talk. So we call these, I think Grant actually came up with this name, this residual cooling flow term for these sort of 1% trickles. Okay, so this is sort of my revised picture of what is happening in clusters, which is still very cartoony. So you start with a giant ball of hot gas, and half the time, nothing happens. So half the time, roughly, clusters just stay hot forever. And so these might be clusters that are susceptible to conduction, and so they just stay isothermal. They might be clusters that just had an unfortunate collision of too many major mergers in a short amount of time. But roughly half of clusters are non-cool core clusters with central cooling times longer than the Hubble time. And so they'll just stay there forever. The other half, they cool, and the cool material comes into the center, maybe initially 100% efficiently. We don't know yet, but I'll tell you that I don't think it does later. And so some gas cools in, but very quickly AGN feedback turns on. And so some gas cools, that gas cools and falls onto the central galaxy, and then onto the black hole, which triggers an outburst. That outburst heats the gas and stops any further cooling. But then if there's no cooling, there's no accretion, and so the outburst stops, right? Now there's no heating, and so cooling starts again, and I'm describing a cycle, right? So the idea is that you go into this cycle that might be governed by some sort of thermal instability, but during every cycle, roughly 90% of the gas is reheated, and about 10% of the gas that isn't reheated ultimately makes it down into stars, because star formation is inefficient just in general. And so 1% of the gas actually makes it into new stars, and that's what we observe. And so if there's people in the audience that simulate galaxy clusters, they'll probably agree this is one of the hardest challenges in simulations right now, is to get this feedback loop right. And I would argue probably no one has done that yet, right? So making realistic central cluster galaxies that feed off these sort of trickles of cooling, and they manage this 100 kiloparsec volume with their AGN over very long time periods. This is really, really tough challenge to get right. But there's great people working on this, so there's hope. So I'm not going to talk too much. This is usually where I would give my talk, is in this rectangle, because I like this cooling feedback stuff. But today I'm going to focus on, the question that, there's no timeline on any of this, right? We don't really know when any of this stuff actually happened, right? Where these initial cooling flows started, when the feedback cycle turned on, when anything, right? There's been a lot of open when questions in the cluster field for a very long time. So the goal of this talk and of sort of my current research is to start putting a timeline together of these major events in a cluster's life. So sort of like a scrapbook of a cluster. So if I'm just going to start guessing things, I'll just guess that AGN feedback maybe turns on around redshift 1. And I'll guess that maybe cool core formation probably happened around redshift 1.5. But there's a lot of other interesting things we'd like to know, right? I'd love to know when every cluster we've ever seen got a third solar metallicity. That's a little bit weird that every cluster has the same metallicity. So when did that happen? Did they all achieve the same metallicity, in lockstep? That would be weird. I'd love to know when star formation was quenched in the cluster environment, and more specifically, when the BCG, the central cluster galaxy, landed in the center of the potential and decided to sort of rule the roost there. I'd love to know when galaxies clusters turned on in the X-ray, when they virialized, and when they sort of separated from this protocluster web, which we sort of define as redshift greater than 3. So these are the questions that sort of keep me going right now. And I'm going to try to give you some constraints on this over the next 40 minutes or so. And the way I'll do that is with this South Pole Telescope Chandra survey. And so these are two fantastic telescopes that are doing really, really complementary work right now, and hopefully will continue to do so into the future. So the South Pole Telescope is at the South Pole. Again, we're not very creative with names. It's a millimeter wave telescope, and it's doing a CMB survey. And what does that have to do with clusters? Well, if you have, a CMB, that's not an if, you have a CMB, okay, that's a fact. And if a CMB photon passes through a cluster on its way to you, it's going to be upscattered in energy. That photon's going to interact with a megaparsec volume of plasma, and that's very energetic plasma, right? So the CMB photon will be upscattered in energy, and it'll arrive at your telescope at a little bit higher energy than you expected. So if you make a 95 gigahertz map of the CMB, you'll find these little bits that are just missing. There's no flux there. You expected there to be flux, but it's not there. And where it is at like 200 gigahertz, right? It's been upscattered in energy, and so it's missing at 95 gigahertz. And these holes are unambiguously clusters. They're point-like, where the CMB fluctuations are a little bit broader. And so it's really, you can get down really deep, and there's, very few systematics in finding these things. So it's a fantastic way to find clusters. And the really nice thing is that it's redshift independent. So as long as the cluster is between you and the CMB, which you can argue it has to be, right? Then it's going to have the exact same effect, right? You're gonna see the cluster with the same amplitude, regardless of where along the line of sight is. And so if we make a survey with the South Pole Telescope, we see every cluster that ever there was along this line of sight above a given mass threshold, and that's a really powerful statement. And so on its own, all we get are these little holes, and we know there's a cluster there, and that's about all we know. And so one of the things that I've been really working at is following up these clusters in the X-ray. So this is a single cluster that has been discovered with the South Pole Telescope. I won't tell you what redshift this is at, and there's no way you could know because we went to the same depth for every redshift. So that means very short exposures for nearby clusters, very deep exposures for high redshift clusters, which means we have uniform signal to noise across all redshifts, which is a thing that an X-ray survey wouldn't have, a blind survey. And so we have 100 clusters followed up with Chandra, and this is what they look like in mass redshift. So we compare to Alexei Vikledin's low Z sample, where we've added a mass cut to match the SZ cut. The red clusters are clusters that are sort of old news now, but these are South Pole Telescope selected clusters from our earlier surveys, and these black points are the latest things that we've observed with Chandra. And the point is that between redshift 0 and 2, we have of order, between the red and black, there's 100 points, and then there's another 30 or so in blue there. But the really nice thing is the selection here. So we're sensitive to sort of the progenitors of these high mass clusters at redshift 0. If you had an X-ray selection here, it would go like this, right? It goes the wrong way so that you're sensitive to low mass things at low redshift and high mass at high redshift, and so it's very hard to do a progenitor study. And so this mass selection is just fantastic for cosmology, but also for astrophysics. Okay, I'm going to move on, speeding up a little bit now. Just before I get into results, I know there's a lot of people here that are really used to looking at Chandra data, and so I want you to recalibrate your mind and your hearts because you're used to looking at things like this, which are just beautiful images and are probably hung up around this building. These are clusters with bubbles, this Perseus cluster, a little bubble there, bubbles here, some sloshing, some cold fronts here, a shock front, cold front, a lot of very interesting structure. And we're not going to be able to do any of this, right? Because we're working in a very, very low signal to noise regime. So the analogy I like, which is appropriate here, because I think this is Randall Smith's image. So let's look at Cygnus A as it looked in 1995 with ROSAT versus Cygnus A as it looks with Chandra. It probably still looks like this with Chandra, give or take. And so when we turned Chandra to Cygnus A, there was just a ton of structure that we didn't know about. And that was completely hidden in the ROSAT data. So let me compare to our highest redshift cluster. I'll just spin this on its side, and they look exactly the same, the ROSAT. Even this little clump, which is creepy, right? But the point is, this redshift 1.85 cluster looks like Cygnus A at redshift 0 with ROSAT. So for people in the room that were using ROSAT and Einstein in these pre-Chandra observatories, that's the science we can do with high redshift clusters, which is exciting science, right? But it's not this science. Okay, so you have to recalibrate your expectations, and so don't ask me about sloshing or cold fronts, because it's just really hard. But there's counts here. This is a detection of a cluster. We can do science with this. And so we're smoothing clusters out of necessity to ROSAT-like resolution, but we do this in a smart way. We do this adaptively, so things like point sources don't smear out and look like cool cores, for example. So the Chandra resolution is not wasted, and I want to stress that for anyone who finds their way onto the Chandra TAC, that even though we smooth these images to XMM-like resolution, we need Chandra data to get at the point sources. Okay, so let me just fly through 4 exciting topics in the next 20 minutes. I'm going to just sort of step through these in the order of interest, I think. So let's start with the evolution of cool cores. Okay, so how did cooling evolve in clusters? So here's 100 density profiles. So these are the density of the intracluster medium, the density of the hot plasma on scales of the virial radius. So 1 is R500, or roughly a megaparsec for people that don't work on clusters. And then this is the density. So this is the electron density of the gas as a function of scaled radius. And these are 100 clusters spanning redshift 0.2 to 1.85, all of very similar mass. So what you can do is you can ask, at a fixed radius, how does the density depend on redshift? The density very strongly depends on radius. So let's just take that out of the equation by just considering a fixed radius. And now we have 100 data points at that radius, and we can plot gas density at that radius versus redshift. This is just a hand-drawn plot. And where this isn't redshift, this is E of Z, which is like redshift. And so we can fit a line to the gas density at a fixed radius as a function of redshift, and we can get the redshift dependence of the gas density at 0.01 R500. Then we can move to different radii, and we can play this game at all radii, and we can ask, at each radius in the cluster, how does the gas density depend on redshift? So if if you're preparing for the qualifier or you study growth of structure, you know that the gas density at a fixed radius should go like E of Z to the power of 2. That's the self-similar expectation. That's if gravity rules the world, C equals 2. So remember that number. If gas density doesn't know about the redshift, if the cluster has no idea what redshift it's at, this C should be 0. Then the gas density is independent of redshift. So let's see how gas density, the redshift dependence depends on radius. So this is a double dependence, which is why I'm going slowly here. So this C is the redshift dependence as a function of radius. At redshift 0, the gas density profile in the core doesn't seem to care at all about redshift. So the central density of the cluster is completely independent of redshift to the degree we can measure it. So I say it's frozen in time. It doesn't change with redshift, and we're spanning 10 billion years in cosmic time here. At about 0.2 R500, this reaches the self-similar expectation where it stays to the degree we can measure it at all radii. And so outside of the core, the gas density evolves. I keep stepping past the camera here, and I'll try to stay more in the center. Outside of the core, the gas density evolves purely self-similar, exactly how it should if gravity is the only important thing, which is great because all of our cosmological tools assume scaling relations that assume self-similarity. So we would like clusters to be mostly self-similar, and that's great, they are. But in the core, this self-similarity is broken. And so there's sort of competing physics here. There's gravity is driving the evolution here, and something else is driving the evolution in the core, which is probably AGN feedback. So let's look at this a different way. So we can go back to this plot, and we can say, well, I know how to evolve a cluster self-similarly. So let me just take the average profile and evolve it self-similarly, so it's at the redshift of every one of my clusters, and subtract that from each cluster. So what I'm left with is the residual above the self-similar expectation. Does that make sense? I hope so, because I'm not going back. So this is the residual above the self-similar expectation as a function of radius. You see this goes out to about 100 kiloparsecs. This is just the central core. And so When I was a starting grad student, all I did was bulge disk decompositions for a long time. And so this was a very natural thing to me to do, to model the cluster as a bulge in a disk and subtract off the disk. And so this is the bulge of the cluster for people who work on galaxies. So this is the excess core density, or the cool core density. So if we look at this plot here, this was our three-dimensional depiction of a cool core. I've just sliced off this cusp, and that's what I'm showing here. Right? So I'm just showing the excess above the self-similar expectation, and I'm showing it for 4 different redshifts, and they're completely identical. So in the previous plot, I showed you that the central density didn't care about redshift. Now I'm telling you, not only does the central density not care, the profile of the central overdensity doesn't care, which should bother you. That's remarkable, right, that happens. So this means that, we think that AGN feedback is very, very gentle and long-lived. If it was too explosive, it would puff up the cool core or destroy the cool core, or you'd get a lot of this kind of breathing, right? But the fact that it's just so well maintained over 10 billion years means it's really just like, housekeeping AGN. It's not, a wrecking ball AGN. And so this is kind of remarkable that the central core is just very, very well regulated for such a long period of time. If you're sharp, you'll notice that I have this legend here where I plot 0 clusters above redshift 1.2, and you might think, well, that's a weird thing to do. So let me plot the clusters above redshift 2, or 1.2, and they are a little bit smaller. So the cores of clusters at around redshift 1.5 are just a little bit smaller than everyone else. And I would bet, if anyone wants to bet me anything, I would bet if we got Chandra time for a cluster sample at redshift 2, it would look like this. Right, so I think we're seeing the initial growth of cores, and then they reach some point where the AGN, sort of shuts off this growth and says you will become no bigger, and that happens at around redshift 1.5, which is kind of neat. Any questions? Do you guys do questions in the middle, or should I wait? I'll just keep going. Yell at me if you want a question. All right, let's talk about interior to the core. So this has been 100 kiloparsecs that I've been talking about this inner cool core. Let's step in an order of magnitude and talk about the inner 10 kiloparsecs. And the reason that's interesting is because, as I told you early on, we see sort of this trickle of star formation in the centers of clusters, what we call sort of residual cooling flows, that represents 1% of the classical cooling flow prediction. And so here's some UV images from Grant Tremblay's work, where he shows, very nice sort of extended star formation, which looks spectacular in the image. But remember, this is 1% of the prediction. This is 1% of what we would like to see if cooling flows were real. 4 years ago, I gave colloquium here on this cluster. I gave a whole hour on basically this little image, because this is the closest thing to a bona fide cooling flow that we have. This is the Phoenix cluster, which has a roughly 600 to 800 solar mass per year starburst at the center, compared to of order 1 to 10 solar mass per year for these guys. So massive, massive starburst at the center of this cluster. Here's the HST image. And so, these are at redshift 0, and this is at redshift 0.6. So if you draw a line between those two things, you might say, well, at redshift 1, maybe everything's a runaway cooling flow, and wouldn't that be neat? So that was, I gave this talk a bunch of times, and people said, well, what happens at redshift 1? So I thought I better stop and figure that out. And so we made this, I'll just skip to the result. This is the star formation rate in the central cluster galaxy as a function of redshift, and just focus on the black boxes, which are just the stacked means. And so as you increase in redshift from 0.2 to 1.2, you have an order of magnitude increase in the BCG star formation rate. So these things that at redshift 0 we call red and dead are 100 solar mass per year or 200 solar mass per year on average at redshift 1, which is a lot of star formation. What was really cool and allowed me to sleep at night is that at the same time, Tracy Webb at McGill did the exact same study completely independently. We didn't know until we published, within a very short period of time of each other, where she looked at infrared selected clusters with infrared derived star formation rates. I used SD selected clusters with UV and spectroscopic star formation rates. We identified BCGs in different ways. Everything was different, and if you overplot my points on her plot, they agree sort of precisely. And since then, her student Nina Bonaventura has done a much better job than either of us independently did, and this all holds up very nicely. So this is 4 systems at redshift 1. These are the near-infrared images of the core, just to convince you that we're actually talking about the BCG, the brightest cluster galaxy. Then if we look with HST at the rest frame near UV, we see a lot of clumpy extended emission. These are all 100 solar mass per year starbursts in the centers of clusters. So if you work on galaxies, and you work on high redshift galaxies in particular, you say, who cares? Every galaxy at redshift 1 is an order of magnitude more star forming than every galaxy at redshift 0. And you would be right? So let's get back to that in a minute. And so the caveat is that everything is more star forming at high redshift. So, don't get too excited about these actual numbers. The more important question is, where do these star-forming BCGs live? And that's where it actually gets kind of interesting. So this plot is both my least favorite and most favorite plot I've ever made. It's really hard to see all the axes that are happening here. But so the point is, we asked the question, where do the most star-forming galaxies live? So that's the first part of making this plot. Where do the 20% most star-forming brightest cluster galaxies live? In what type of clusters? At redshift 0, roughly 100% of the most star-forming brightest cluster galaxies live in relaxed clusters. Okay, that's not surprising. That's what I told you on slide 2, right? That in the centers of these cool core clusters, we always find these residual cooling flows. And so we see star formation in clusters that are relaxed, that look like this, that have these cool cores. If we ask the same question at redshift 1, we find that 100% of the most star-forming BCGs live in what we call disturbed clusters. So these are the X-ray images. This is very clearly a merger. This is almost certainly a merger. This is definitely two interacting clusters, right? So these are all merging clusters, and that's where we find the most star-forming brightest cluster galaxies at high redshift. This is the X-ray peak in the plus sign here. This is the starburst BCG here. They're offset from the peak compared to low redshift BCGs, which sit in the center of the potential. And so we think that this star formation at high redshift is being driven by merging activity, by interactions with galaxies coming in as part of the merger, whereas at low redshift, this star formation is being driven by residual cooling flows. The reason is, at low redshift, if you have a group fall in, when it gets to the center, it doesn't have gas. So if it interacts with the brightest cluster galaxy, when it falls in, it's a dry merger, right? Because galaxies and clusters don't have gas at redshift 0. At redshift 1, if you bring a galaxy in to the center, it probably has gas. Everyone has gas at redshift 1, right? All the galaxies, at least. And so, there's just a higher probability of wet mergers at redshift 1, and there's going to be a higher probability of galaxy mergers when you bring, a group into the center of the cluster. So this leads us to this picture. So this is the specific star formation rate. Now I've normalized the star formation rate to the stellar mass. So now 100 solar mass per year is a little less interesting because these are also the most massive galaxies in the universe, right? So 100 solar mass, it's all relative. It's not as big of a number. The boxes, again, are the brightest cluster galaxies, where I've added some low Z surveys for comparison. And so there's this, steep rise. These are typical cluster galaxies in purple and typical field galaxies in green. So cluster galaxies quench faster than field galaxies. We know that. But BCGs quench faster than both until low redshift, where they start to flatten out in their evolution. And so I would argue, on the basis of 7 data points, that we're seeing sort of a two-phase evolution of these BCGs, where very early they're quenched. Very early you have all this star formation due to gas-rich mergers at the center of the cluster, and you're building the BCG. And then very quickly that star formation quenches until you reach some point where, if you quenched further, or the point where basically this residual cooling flow, this 1% trickle of cool gas, is the dominant source of cool gas, and it dominates over infalling galaxies, right? And so at this late stage, this trickle of star formation is actually the dominant source of fuel, or this trickle of cool gas from the cooling flow is the dominant source of fuel, and I call this sort of the life support mode for the BCG. It'll continue to form stars basically forever because there's so much fuel in that hot halo. So if you fast forward maybe 10 billion years, BCGs might be the most star-forming galaxies in the universe because just no one else has gas at that point, which is kind of neat. You can backtrack if you dare and extend this fit back to redshift 2.5. The point of this is just to say that up here at redshift 2.5 or so is where protoclusters are starting to condense into clusters. And if you ask what's the star formation rate in the inner 100 kiloparsecs of a protocluster, you get these numbers up here. which provided in these papers. The idea is that all of this stuff in the inner 100 kiloparsecs is going to become the BCG, right? And then you start to get this rapid quenching after this assembly phase. So the goal of the next, half decade or so is to basically fill in this part of parameter space and ask, when does the peak star formation, when is the peak assembly time of the brightest cluster galaxies? But we're starting to get there, which is pretty exciting. Okay, this one's a quick one, which is good because I'm running out of time. Let's talk about the metallicity evolution. So I told you, no matter where we look in the local universe, we see a third solar metallicity in the ICM of basically every cluster once we get outside the core. So we can ask, what is the evolution of this number? Is there evolution in the intracluster medium metallicity over 10 billion years? The answer is there is none, right? So there's, which is a little bit boring, but it's kind of neat. So this is, if you parameterize the metallicity, which is capital Z as a function of 1 plus Z to the minus gamma, and you fit all of the clusters simultaneously in a big Monte Carlo package, you get this gray contour. So this is the tightest constraint we have on the evolution of the metallicity in the intracluster medium, and it's fully consistent with 0, right? And so we see no, yeah?
You don't believe the red contours?
I believe that's what they measured. Yeah. So there's a lot of selection that goes into the scatter here, right? If you have a sample that's dominated by cool cores, you're going to measure a higher metallicity because these are not quark-sized metallicities. So I don't want to disparage any of these authors. I believe we have a very, very clean selection, and so I trust this gray contour implicitly. The point is, we see no metallicity evolution, and the formal constraint is that at least 2/3 of the metals were already in place at redshift 1. That's the limit that we get by the fact that this isn't infinitely narrow, basically. There's some evidence for late enrichment of the cores. I'm not going to go into this because I don't know if I believe it, but it looks like the metallicity peak that we see in the centers of clusters might have come in since redshift 1. So if that turns out to be true, I said it first. If it's wrong, I didn't talk about it too much, so just to be safe. Okay, so let's finish up with this one, which is kind of a cute result. So we'd like to know the merger rate of clusters, right? That's an important thing we'd like to know. You could actually constrain cosmology pretty well if you could actually observationally say precisely what is the merger rate of clusters, because they're the biggest peaks in the cosmic web. And so we wrote this proposal to observe the most distant clusters, and I think I used the phrase in the proposal, we expect all of these to be mergers because the merger rate above redshift 1 is so high, but that'll still be really interesting. Because I usually don't work on mergers, so I had to convince myself that that'd still be interesting. So if you go ahead and measure the fraction of clusters that are morphologically disturbed as a function of redshift, this is what you might predict, right? This is the halo merger rate for the most massive halos from Fakuri et al. 2010. So this is what you might expect if you go out and make this measurement. So if you're really sharp, don't yell out the endings of the story, and you're sharper than I if you see where this is going. Before we did this, we had to actually explain what we mean by disturbed. And so typically this has been done by eye. If it's not done by eye, it's done using, for example, a centroid shift. So you put an aperture on a cluster, you measure the centroid, then you grow the aperture and you measure the centroid, and then you grow the aperture and measure the centroid. And if it's bobbing around, it's probably not a spherically symmetric cluster, right? So that's what we call the centroid shift. It turns out the centroid shift is highly dependent on the signal to noise, right? Because that centroid is going to bob around onto noise peaks as well. Likewise, people use power ratios, which is also highly dependent on signal to noise. And so we knew we had this, not very great data. And so, it's great in some ways, but it's low signal to noise. And so we wanted to design a morphological indicator that was immune to signal to noise. And so a great student, Danyar Nurgalev, who was a Harvard PhD just a few years ago, we worked on this together along with Chris Stubbs and Alexei Viklinin. And we built this thing which we call a photon asymmetry, which is just a fancy way of saying, how far from an azimuthally symmetric distribution do we have in the photon? So we say, we assume an azimuthally symmetric distribution, we measure some distribution as a function of azimuth, we do a KS test, are they the same? That's immune to the number of counts, right? That's just a clean statistical test. And you measure the same asymmetry as a function of counts. What happens is the uncertainty blows up. if I actually plotted the uncertainty here. But the actual measurement isn't dependent on the number of counts, and that's exactly what we want. Side note, this is great for deep surveys where you have very little data on the high redshift clusters, maybe 50 counts on a high redshift cluster and 5,000 counts on a low redshift cluster. If you're doing a morphological comparison, you better be using something like this, right? We also tested, because this was in preparation for eROSITA, this is independent of the size of the PSF as well, which is handy. Okay, so we have the tool, so let's go out and make the measurement. So this is the disturbed fraction as a function of redshift. We have some points from Adam Mance here, and then this blue region are our data. Okay, so just for comparison, the Fakuri et al. Intersected with 0.8 at redshift 1.5. That was the merger rate calculation. So we basically measure no redshift evolution in the morphological distribution, which was really weird. And then I sat down and thought about it for about 10 minutes, and it became clear that this is not what we're measuring. This is the halo merger rate. We measured the number of things that at this moment look disturbed. And so what we need is a time scale. We need to know how long after the merger do they look disturbed. If that's 1 day, we will never see a merger, right? If that's a Hubble time, every cluster will look like a merger, right? And so what we actually need is the crossing time, which looks like that. And if you multiply the two, well, gosh darn, don't they agree with the data, right? So that's, this was kind of a very fun thing that made me appreciate hindsight a lot. And so what my appeal to the theorists in the audience is that this is the wrong time scale, right? You guys know what the relaxation time is for clusters. So instead of giving me a merger rate, you can actually give me a disturbed fraction, and I can plot it up against the data, and we can do some science, right? So the merger rate is no good to an observer unless I know how long after it looks like a merger. So this was kind of a fun result. So the moral of the story is that clusters at redshift 1.5 look just like clusters at redshift 0 in terms of their morphologies. These are maybe hard to look at. If you look at the insets, they're a lot smoother. The point is that you should see things that look like cool cores, right? This is a fairly cool core, and things that look like, offset mergers, right? All types of clusters are represented in the same fractions at redshift 1.5 as they are at redshift 0. So just about out of time, so let me just give you the ta-da. So this is, what I showed you earlier, and we're starting to actually get pretty good constraints on this. So I didn't talk too much about AGN feedback, but Julie Hlavicek-Larondo has a nice paper from 2015, and I'm doing some work right now with Alistair Edge on pinning down when AGN feedback started, and it started certainly before or around redshift 1.5. I showed you earlier, I think cool cores probably formed between 1.5 and 2. The metal enrichment definitely happened prior to redshift 2, maybe around redshift 2.5, which was the peak of stellar winds. The star formation definitely peaks above redshift 1.5. I would guess, much higher than that, probably around the protocluster regime, which is between 2.5 and 3. And I haven't made much progress on these, but I'm still young. So if you invite me back 4 years from now, I'll probably talk about what's in these red boxes. This is what we're working on right now, is really pinning down how these central cluster galaxies assemble and when they assemble and what are the important physics, and precisely when this feedback loop sort of tightened up to the extent that it is today. These are where we're putting our money right now. So just final couple slides looking ahead. This is where we exist right now, with the exception of eROSITA. So this red curve, these red points are Planck-selected clusters. Black points with colors around them are SPT-selected clusters. Blue points are the second generation SPT experiment, which extends deeper in mass, which means it gets out further in redshift because it takes time to build mass, right? So these clusters are all observed. We're starting to get Chandra data on some of these low mass, high redshift clusters, thanks to the HRC folks, as well as the ACES folks. This was a joint GTO program. And we're just starting to understand what's happening in these low mass, high redshift systems. We have a ton of radio data. All the green circles are radio observed clusters, and we can start to look at the evolution of AGN feedback, which is exciting. But this is what gets me really excited. So these blue points now are the third generation South Pole Telescope experiment, which started this year. It's not going as well as they hoped, but it will reach this point in a few years. It's a long survey. So this is roughly 10,000 clusters extending out to whenever clusters became clusters. It's going to probe down to 10 to the 14 solar masses, and so it's going to probe out to redshift 3 if clusters exist there, which is exciting. This green region is what we have done with Chandra, basically. This red region is what we can do with eROSITA, which is exciting, right? But it doesn't get us much of the stuff we really care about, which is the redshift greater than 1 clusters. So we're working hard on convincing people that this is a valid way forward of combining the strengths of Chandra and XMM to make sort of a super observatory akin to something like Lynx or Athena, but currently existing. And so you can imagine doing a high-Z REXTEST survey, a high-Z representative survey of all clusters where you just limit your field of view to 100 square degrees instead of 2,500. And you sample roughly 30 clusters above redshift 1 in a representative mass sample. That's something that we can do now with proper support, which would be just a beautiful sample for cluster evolution, right? Those become things like, Virgo and Coma and Perseus. But really, we're waiting on Athena and Lynx to do the exciting science here, which is still a little ways away. So we're at 450, so I'll leave my results. But these are all just one-liners. Cool cores have not evolved in size, shape, or absolute mass in 10 billion years, which should bother you. And it's kind of crazy that AGN feedback is doing such a good job of maintaining the structure. High-Z brightest cluster galaxies are star forming, so if you build a survey to find high-Z clusters, don't look around luminous red galaxies. You should look around starburst galaxies at high redshift. The bulk of the metals in the intracluster medium came in before redshift 1.5, probably at the peak of star formation around redshift 2.5. And not all high-Z clusters are mergers, as you might expect, because the relaxation time of high-Z clusters is shorter than it is today because they're more compact. So I'll just stop there and take your questions. Thank you.
Very nice talk. Questions?
I have a question regarding your statement a few slides back that everything at redshift 0.601 was star forming, like it was related to the star formation BCGs.
Mm-hmm.
In fact, I would argue that it's not the case, because by the time, if you have an intracluster medium, by the time a massive galaxy reaches the cluster center, it will be Ryan pressure stripped. So at redshift 0, right now, it's impossible to merge like the Able 478 BCG with this gas-rich galaxy, just because there will be no gas left by the time it reaches the center. It's not the property of the galaxy that is falling on, but rather than a property of a cluster that strips it.
So I would argue that it's not that easy to strip a molecular disk. It's not obvious that molecular disks get stripped on their first infall. But more importantly, when we look at redshift 1 BCGs, they all look like wet mergers. I agree with you that
maybe there's no intracluster medium.
No, because we see them in the X-ray, right?
Not at this amount.
Yeah, so the density is high, right? So, I mean, the density is the same. These are clusters spanning 10 billion years. They all have the same central density. So the density is high.
Then how can you explain it?
Yeah, that's why we do this, right? So I don't have an answer. My guess would be that we think it's easier to strip a molecular disk than it actually is. And I think what we're actually seeing is not individual galaxies falling in, but in fact we're seeing groups or clusters falling in. And so if you bring a whole group in, maybe it doesn't strip the same way because it's shielded by its ICM, which is stripping as it falls in. That's my guess. If you bring a group in, by the second passage, it's going to be a BCG on BCG collision. And if they're protected by their own IGM or ICM...
So you think it can shield?
I think that, or I know that I see wet mergers in the centers of redshift 1 clusters. That's how I think it could happen. And the clue is that these all look like mergers in the X-ray.
I had a question about the feedback. I think you were discussing something that you were calling soft feedback from the AGN.
Okay, I hope I didn't say that. I didn't mean soft.
Maybe I didn't. Maybe I'm not using the
Sure.
terminology correctly.
Oh, I was saying like gentle feedback.
Gentle,
Yeah. Okay.
Gentle.
Yeah.
Okay. So gentle feedback. Is it possible that some of that comes from stars? So you're having star formation, you have X-ray binaries that are forming, supernovae, etc. So could some of that feedback be associated with the star formation itself and not necessarily coming directly from the AGN? And if so, what do you think the fraction would be?
So I think very little of it's probably due to star formation feedback, assuming you mean supernova feedback. So the supernova rate in the core is...
X-ray binaries.
Sure. Yeah, so the short of it is, the X-ray binaries are going to provide similar hardness photons to the ICM, but way suppressed. So those X-ray photons are already living there, right? It's, you can't heat a 2K UV gas with 2K UV photons, basically. And so we don't think it's radiative feedback in any way. We think it's all mechanical. And I'm bad at going backwards in slides.
That's okay, I know.
But so there's this really nice correlation between the radio jets and the cooling luminosity, and they agree very well. So there's almost no need for an additional form of feedback. There's definitely some energy coming in from those, but I don't think it's driving.
I was just thinking that it might be correlated, not separate or even happening at necessarily a separate time, but because you're bringing this matter in and you're having the star formation and the AGN activity is going on all together.
Right. So certainly in some systems, so for example in Phoenix, I've gone too far, almost there. So in this system, it's hard to see because the lights came back on, but all of this, you can kind of see if you squint that there's like a wind being driven up in this direction. That's probably a starburst-driven wind. So this is a system, maybe the only system where it looks like the starburst is actually quenching the cooling, but that's because it's just a crazy system. We're typically talking 1 solar mass per year, and it's very small, low energy stuff. Yeah.
Well, that could be an ionization kind of an AGN.
It could be. Yep. Yeah. It's certainly a highly ionized wind of some sort.
Right.
Yeah.
Martin?
So you have this very smooth accretion rate for 10 billion years. So did you work out the amount by which the black hole would have grown at the center? And so how small was it back then? Is that interesting?
From the cooling?
Yeah.
It's negligible. So
it grew almost nothing.
Compared to the growth due to mergers, it grew almost nothing. So, so if you look at, assuming black hole mass traces the galaxy mass, the galaxy grows by a substantial amount between redshift 1.5 and 0. The amount of that's due to cooling is less than 1%. It's almost all dry mergers.
Aleta?
At redshift higher than 1, you start seeing quasars. And you didn't say anything about quasars and clusters, and you know that they are various. So are you excluding them? Are you not detecting them? Are you biased in any ways when you're looking at this evolution of redshift?
So in our sample of 100, there's one cluster that the central galaxy is a quasar, and it's on the screen right now, so it's Phoenix. That's one cluster for which the X-ray point source brightness outshines the ICM. Julie Hlavchek-Larondo is digging into the data a little bit further than my qualitative statement, and she's quantifying the X-ray bright fraction of central AGN, but it's a very small number. It's higher than at redshift 0, but these are not. I wouldn't say any of these are quasars.
I'm just wondering about the selection using Sunyaev Zel'dovich. This doesn't affect what you find.
Right, so it might be that X-ray surveys find a higher fraction of high Z quasars because they contribute X-ray flux, right? So we are not selecting against central quasars. So there's almost no way, unless nature is extremely unkind, that quasars in the centers of clusters could mask the SE signal. So what would need to happen is that radio loud quasars get brighter faster than 1 over d squared, and they have a flat spectrum. And that would just be, that could happen, yes, that could happen. We don't think that's happening, but we hope that's not happening, I guess. But that would be really severe. And if that was the case, I think actually the argument is, if that was the case, we would, if radio loud quasars got bright faster than 1 over d squared, that's what we would see, right? Because their apparent magnitudes would be brighter than nearby AGN. And so we would just see a sky full of redshift 1 radial at AGN, and we don't see that. So I think that argues that that's not the case. Tony probably has the answer to this, actually.
Yeah, well, this has been studied, and if you do a deep centimeter wave image of a cluster of galaxies, there's a good point, 8 or so, you'll see half a dozen detectable sources that have a few hundred nanojanskis brightness, and they're about an order of magnitude away from killing off the SZ effect at millimeter waves. They're bright at centimeter waves, but they're just not bright at millimeter waves. So at least for clusters with redshift less than 1, the estimate is that 3% are missed because there are bright radio sources in the middle.
And those 3% are primarily at low redshift. Yeah, because the closer it is, the more the radio flux affects the SZ signal. Because the SZ signal is not redshift dependent, and the radio flux is strongly redshift dependent. Right. So the very hand-wavy way to think of this is Phoenix is both the most radioluminous BCG we know of and the dustiest BCG we know of. Both of those things should fill in the SZ decrement, and we calculated how much, and it's of order 1%. So the most extreme core we know of adds a 1% bias to the SZ signal.
I did have a question. So the origin of the intracluster gas, right, it has a metallicity of 0.3, and also much of it must be primordial. And so how do things arrange themselves so that the gas coming out of the galaxies that have metallic metals in it always matches the amount that's coming in primordially to give you a mixture of 0.3?
So if I had the answer to that, I would have led with it. But the short answer is that I think there's probably not a lot of filament gas with 0 metallicity right now. I think probably much of the universe is a third solar right now, and so the stuff coming in along filaments is probably a third solar or maybe 0.2 solar. And so I think there's probably not just a lot of 0 solar metallicity kicking around anymore.
And then there's not a lot of gas actually coming out of the galaxies into
That's
the
right.
cluster.
Yeah, it's hard to push the galaxies out of the disks, or push gas out of the disk of galaxies in clusters because you're pushing against a pressure. Right.
I think we should thank Mike again. And